learners. Today we're going to be continuing on Unit 2 about electricity and magnetism. Our class rules: please be respectful, please participate, please follow all of the bare expectations as we go forth in this Unit 2 learning. Some things you'll want to focus your learning in on and make sure to include in your Unit 2 notes are explaining how objects become electrically charged by gaining, losing, or sharing electrons, being able to explain magnets and their attraction or repulsion, understanding both a magnetic field and an electric field, and understanding magnets and electromagnets. And as we move forward tomorrow, you will understand motors and generators and whatnot, bridging on our learning from conductors and insulators. So let's start today off with a warm-up. Go ahead and let me know in the chat, how does lightning form? I'm going to give you a couple of minutes here and Engagely. As we review the answer to that warm-up, lightning is formed through a phenomenon known as electric discharge. This is a phenomenon where the release of electricity comes from somewhere it's stored in a source. Go ahead and peruse that third bullet point before we watch a video on how exactly it is that lightning forms.
The image is unmistakable. Lightning is one of the most incredible natural phenomenons, and one that scientists are still learning about. It's a common occurrence during summer when the heat of the day is broken by strokes of lightning. Worldwide, it's estimated lightning occurs 50 to 100 times a second. The greatest concentrations of lightning strikes are in Central Africa, the Himalayas, and South America. Lightning is often seen flashing between storm clouds in the earth. The bursts of light are pure electricity. Scientists don't fully agree on what actually causes the electrical charge to be dispersed, but it is generally thought that lightning often occurs within the downdrafts and updrafts of thunderstorms. Lighter particles moving toward the top of clouds become positively charged, while heavier particles hitting toward the bottom become negatively charged. When the positive and negative charges grow large enough, lightning is released between these regions. Most of the lightning takes place within the cloud, but some strikes the earth in bold flashes. In these cases, the charge escapes the cloud, making a branching path that reaches for the ground. The energy of the lightning strike contains hundreds of millions of volts and lasts only a fraction of a second. What seems to be a single flash is actually a series of return strokes of electrical energy reaching back up into the clouds. The path reaches temperatures of around 50,000 degrees Fahrenheit. This extreme heat creates the booming thunderclap as excessive pressure within the lightning path expands at supersonic rates on return strokes. In the U.S., lightning occurs most often in Florida. Its hot, moist climate is perfect for creating thunderclouds, which produce lightning. But lightning is a deadly natural phenomenon, taking nearly 100 lives a year on average in the U.S., more than hurricanes or tornadoes. During electrical storms, experts warn that people should seek shelter inside a building or hard-topped automobiles, and if caught in the open, avoid high ground and isolated trees. Lightning is a powerful force of nature, and one to be cautious of. Guys, I'm about to...
Now that we understand lightning, we are more broadly going to look at electric current. I will have played that video for you in class as we move on. Go ahead and take a couple minutes to look at, I'm not sure if I spelled separating right. Let me look that up. On this list, there is 11 sentences. Some are referencing electricity and some are referencing magnetism. See if you can take a couple minutes and match them correctly. And I will take the couple minutes to see if I spelled separating correct. No, I did. That's separating. Here are the answers. Again, I will give you some time in Engagely to check them and add it to your notes. So electricity applies to 2, 3, 6, 8, 10, and 11. That is that electricity flows through circuits, not magnetism. Electricity powers a light bulb. Electricity is produced by a rotating magnet. Electricity is lightning. That's a natural form of it. Electricity flows through metals but not plastics. We learned that yesterday with conductors and insulators. And electricity is, to be exact, flowing electrons, which happens through a conductor, such as water or metal, as each little particle transfers an electron back and forth to transfer the charge through the medium. Magnetism is iron surrounded by a flowing electric current. It is the reason compasses work. It is the cause of two objects being attracted to each other or repelled, and Earth is one giant example of a magnet. I'm going to give you 3 minutes in Engagely to do a little vocab review here for protons, magnetic field, electron, electromagnetic, electric switch, electricity, magnet, and electric current, and to see which definition they match up with. I'll reveal it in probably 2.5 minutes. I feel like that's an adequate amount of time. See if you are correct. I'll probably just give you like a minute, minute and a half here to check if you correctly match those vocabulary terms. How do electric charges interact? So this is going to look very similar to a slide I showed you yesterday on magnetism. This here. Here are magnets attracting. But if you wrote it down, what that is the law of electric charge. So there is a huge similarity going on there between magnets and electricity. If the law of electric charge can apply to magnets, then how different are they? I'm going to give you 30 seconds to read this on your own, and then we will move on. This, by now, should be common sense. Okay, don't think too deeply on it. In our chemistry unit, we started to review what it is that an atom looks like. In its center, in the nucleus, there are protons and neutrons, positively charged and neutrally charged. So there is a positively charged center of an atom. And then in my 819 class, Isaac said it best. He said, what are those little guys running track around the center? So there are electron shells, which you can think of as the track field going around the center or nucleus of that atom. And those circles that represent the different lanes of the track field have a predetermined number of electrons that are allowed to live in them. So mostly it's 8. So you will fill up a whole track field or a whole electron, and then when you run out, because each atom specifically has its own number, it might have 8 electrons, it might have 14 unless it's bonded. That outer shell of electrons will not be full to 8. It might have 1, it might have 2, and this is what helps us know what an element will, it kind of predetermines what it'll bond with, which is why hydrogen bonds so easily. It just has 1 electron. 1 electron in its outer cloud and 1 electron period. So it's bonding with everybody. So if somebody has 6 in their outer shell, which means they're missing 2, 2 hydrogens can hop on and bond there. Or an element that has 2 electrons in its outer shell. I'm hoping that's starting to make a little bit of sense. Here you can see that image exactly what I was talking about. In the center, 11p, 11n means the same number of protons, same number of neutrons. It is a positively charged nucleus because neutrons are neutral. You can see there that first shell of electrons is 2, and then that next one has 2, 4, 6, 8, and then that last shell just has 1. I'm referencing the picture on the top, 1 outer shell electron. So that one is going to balance wonderfully with any element that has 7 outer shell electrons or less, and it will bond 1 or multiple of it with its 1 outer shell electron to either give or share. If you had a chance to peruse the electrical charges paragraphs there on the left, the only takeaway there, because we already know protons are positive, neutrons are neutral, and electrons are negative, is that we learned a new word called an ion. Okay, so that is if there's an unequal number of protons and electrons, and therefore it's not a neutral particle, it is a charged particle. That would be an ion. So in that bottom image, the way there are 11 protons and 10 electrons lets us know that it is an ion, even though in that image we are losing an electron. How strong is the electric force? The force between charges depends on the amount of charge and the distance between them. So this force of attraction does change. It's not the same for everything everywhere. You can kind of contribute or attribute that to the similarities we were doing with, gravity or kinetic energy. Not everything has the same kinetic energy. If two things have the same mass and were given the same push, they'd have the same kinetic energy. So the same thing applies to force. If they have the same charge and they're the same distance, then they would have the same either attraction or repulsion, but it is different. You've definitely felt a stronger magnet versus a weaker magnet. It is dependent on 2 conditions: the amount of charge and the distance between them. I'm going to give you 2 minutes more to read about these lemons here. Moving on, we know already that conductors carry current, but do a quick review. In a wire, as you can see there on the right, the inside, the copper part, is what carries the charge. The outer part that is plastic or rubber is an insulator. That way we are able to touch the wire and install it, move it without being electrocuted. Insulators, we did begin to learn about them yesterday, stop the flow of current. So that was plastic, rubber, the brick, a piece of rock. I'm going to give you a minute and a half here to read this slide. Now, what it is that makes these electrical currents flow? A couple slides ago, you read that rubbing together transfers those negatively charged electrons. That's static electricity. Chemical reactions come from a battery. So this is where we're going to start to transition our learning here from just magnets and electricity into specifically motors and generators, things that make or store charge until you're ready to use it, like a car, golf cart, lawnmower, etc. Okay, we're going to stop here for Tuesday. We're going to continue on with motors and generators on Thursday.